Welcome to the Python Programming tutorial series for Climate Mathematics Theory and Applications, Chapter 10, Advanced Python Analysis and Plotting. In this video, we will do a reanalysis example using NCEP/NCAR climate data to create EOFs and visualize principal components. Let's begin with section 10.3, from climate data download to EOFs and PC visualization, an NCEP/NCAR reanalysis example. First, you are going to have to download the following dataset from NOAA into your active folder. You can find this data from the highlighted URL. Once that data is downloaded, we're going to go ahead and access that data using the netcdf package with the dataset function. You're going to import that air.mun.mean.nc file. We are going to import this using it in only read mode. Once that is downloaded, you are going to define the variables. You are going to use your dataset name followed by the word variables with which variable you would like to import. We're going to import the longitude, latitude, time, and air data using this method. We're going to also import the time units. Rather than using the air variable, we're going to use pre-CNC as our air variable, which represents the air temperature in this data set. Moving on to figure 10.5, we're going to plot the data along the meridial line. First, we need to define an X variable, which we are going to call NC_X, which is going to be the line space between -90 and 90, with 73 points in between. Then we are going to define our Y by listing the values in the pre-CNC dataset following the 0th index by all rows in the 71st column. We're going to reverse this list, and then we are going to go ahead and plot our data. We're going to plot this data using the PLT plot on our NC_X by our Y variable. We're going to use dots in the color of black on our plot. Set our X label to latitude, set our Y label to temperature, degree C. We are also going to rotate those Y ticks so then they show up in a vertical fashion, and we are also setting our title. I would like you to notice that we do have quite a long title, so we are sticking in a \n, which will create a new line in our title. Wrapping that whole block with a PLT show, we do get this NCEP/NCAR reanalysis surface air temperature degree C along the meridial line at 180 degrees east. Now we are just going to continue to do some computing on this data set. First, we are going to reverse that list that we just created to make sure we are not modifying our pre-CNC variable. Then we are going to verify that we do have our original shape, which is in fact 826 by 73 by 144. In this next block of code, we are going to be defining some variables and building some functions. We are going to define our pre-CST as our 0 matrix that has 10,512 rows by 826 columns. Next, we are defining temp as the reshaped version of our 0th index in our pre-CNC, all rows, all columns, and we are reshaping this into a single array That is 144 times 73 of size. We're going to go ahead and print that shape of that temp variable. We also are going to print the first 6 values in that array. We're going to go ahead and make some reshaping functions, defining this function as spmat, and it will take x and y in its parameters. We're going to enter this for loop for I in range from 0 to 826. We're going to enter that y matrix and reshape our x matrix based on the ith index with all rows, all columns, and we are reshaping it into a single array that has length of 144 times 73. Finally, returning that y matrix out. We are using this function and saving the result as pre-CST2. We are operating that spmat function on our pre-CNC and our pre-CST matrices. To verify its shape, we are going to go ahead and print out its shape. Next, we are building a lat and long for 10,512 spatial positions using a rep function. We're going to define this function rep, and it will take parameters x, y, and n. We're going to enter a for loop, and we are going to append y to the back end of our x array, and we are going to return our x array. We're going to go ahead and make an array out of 1, 0 using the np0s function. We're going to go ahead and make a lat variable using our rep function on ara by lat vals 144 times. This will go in and append lat vals to our ara variable 144 times. We're doing a very similar method for our long variable. We are going into our rep function and we are appending our long values to ara 73 times. We're going to go ahead and print long out as well. To create the reconstruction function, we are going to define it as recon with no parameters. The result will be set equal to long, and then we are entering a for loop that spans from 0 to 143. We are setting the result equal to the appended version, where we are appending the rep function on ara, which is appending long vals 73 times to ara, and then we are appending this new array to our result, which was defined as our long variable. Finally, returning that result. We're going to go ahead and set the result of our recon function equal to long2 and print out the last 6 entries. Next, we are creating an array with the first 2 columns of lat and long, with 826 months spanning from 1848 to 2016. We are first going to define GP, CP, ST underscore as the column stack between lat and long 2. Next, we are going to use that GP, CP, ST underscore, and we are column stacking that new data frame against our pre-CST2. And we are going to name this column stack GP, CP, ST. This matrix will be used in most of the computations in this chapter. Reviewing all of our print statements that we retrieve after running this block of code, we do get a temp shape of 10,512, seen highlighted on the screen. Now we can see that the highlighted portion on the screen is the first 6 digits of our temp array. Next, we printed out the shape of our pre-CST2 variable. Next, we printed out our long variable, which was an array of zeros. Lastly, we printed the last 6 entries of our long2 variables, which can be seen highlighted on the screen. Moving on, we are going to create an array of all ones for the days of the data. We're going to create a month function, a year function, and a time function in the next block of code. Starting with an array full of ones, we're going to name it ones, and it is going to have size 826. Next, we're defining a function to create a list of months repeating to match the size of our data. We're going to name this month function, and we are going to first start off with a month array variable, which is going to hold 10 at the beginning of it. Then we enter a nested for loop, which will dictate that we are appending to our month array the integer dictated by our J range. Once this nested for loop is complete, we will enter another for loop where we are going to now append our integers dictated by our K loop to our month array, finally returning that month array. We're going to use this month function to create the variable months seen highlighted on the screen. We are going to use our month function to create the variable months seen highlighted on the screen. Next, we are going to define a function that creates a list of years to match the size of our data. This function is called year function. We're going to start off in a very similar fashion with a 0 array, going into a nested for loop to append all of our indices to our year array, then entering another for loop to append the year 2018 to the back end of our year array, finally returning our year array. We're going to use this function and name its result years. Moving on, we are going to define a function that pairs a string version of our year and month arrays with a dash in between them. These will serve as our column names for our data. We're going to name this function tmfunction. We're once again starting with an empty 0 array, and we are appending to our empty array the string of the years plus the string version of our months at every single index found in those arrays. And we are finally going to return our empty array once this for loop is ran. We're going to use this function and name the result tm1. tm1 will be the year and month array with the dash in between. We're going to add lat and long columns to the beginning of our column names. We're going to name this tm2, and it will be the appended version of our lat and long arrays appended to our tm1 variable. Moving on to inline 83, we're going to use the pandas data frame to match the column names with the data. We're going to name this GPCPST, all caps, and we are going to go ahead and convert our GPCPST to a pandas data frame using the columns dictated by tm2. We're now going into creating some variables that we will be using to compute the area weighted anomalies. We're going to go ahead and create a monj variable that uses the NP array function with a range spanning from 0 to 826 that is skipping every 12 numbers. We're next going to create a GP-CP DAT matrix using the GP-CP-ST matrix that was created above, locating all rows but only columns 2 through 826. Now we are going to go ahead and define a GP-CP-J array that will allow us to go into the matrix that was created in the line above, only indexing through the MUN-J columns. Using this GP-CP-J matrix, we are going to grab the means from every column in this and name it ClimJ, representing our climatology of January months. Now I'm going to go ahead and create some desired functions to compute the standard deviation as well as the anomaly matrices from this data. The highlighted function will create a row standard deviation for us. We're going to enter a result array, which is originally an empty array. Then we're entering a for loop where we are going to append each standard deviation of that GP-CP-J matrix, where we are grabbing each row in it and computing the standard deviation and adding it to our result array. We're going to go ahead and follow this standard deviation function with our definition of STJ, where we are taking the GP-CP-J.std, which is that standard deviation on axis 1. You can use this highlighted function to grab the standard deviations. However, our function that is seen highlighted will do it in a similar fashion. Next, we are defining an enum.j function 2. We are grabbing the result from the data frame of all zeros that has columns dictated by TM1 on our MUN-J variable. Then we are entering a for loop and setting each column of our result matrix equal to the GP-CP DAT location on all rows with MUN-J columns, dividing, subtracting the ClimJ matrix from that, and finally dividing our SJ values from this result. Finally, returning that result matrix and following that with running our function and naming the result enum.j. We are going to go ahead and define an enum.j function 3, which will be dictated in a very similar fashion, setting up a result matrix made out of zeros with columns TM1 on index MUN-J, and then entering a for loop, which each column in our result data frame will be set to the square root of the cosine of our GP-CP-ST matrix location of all rows, the first column of times pi divided by 180, and this result will be multiplied by our enum.j that was just created from our enum.j function 2. We're going to return this data frame and go ahead and use this function and name the result equal to enum.aw. Now we are going to go into computing the SVD from the area weighted anomaly matrix, which is that anom-AW matrix we just created. We're going to set U, S, and VH equal to the SVD computation on that anom-AW matrix with a full matrices equal to false. We could go ahead and print out the resulting shapes of our SVD computation, which results in a U shape of 10,512 by 69, an S shape of 69, and a VH shape equal to 69 by 69. Going into figure 10.6, we're going to go ahead and create some variables and plot some figures. First, we're going to go ahead and start with our X values, which is going to be a line space between 0 and 70 with 69 digits in between. Next, our Y values, which is going to be 100 times our S matrix squared divided by the sum of our S matrix squared. We're going to create two subplots using that PLT subplots function and setting those subplots equal to Fig and AX1. Going into our first plot, we're going to scatter the X vowels by Y vowels using a circular marker with edge color black. We also want the line corresponding with these scatter points, so we are using the X vowels by Y vowels in the plot function. This line will also have the label percentage variance. We're going to go ahead and set our Y label equal to percentage variance, our X label equal to mode number, and set some of our tick parameters with axis equal to Y and our label color equal to black, which is dictated by the K. We're going to twin this X axis on our AX1 variable and set it equal to AX2. Moving on to plotting our data on our second axis, we are going to go ahead and use some scatter functions to scatter our X vowels by the cumulative sum of our Y vowels. This will have a color of blue on our plot. We do want a line to go along with these scatter points, so we are using the plot function on our X vowels by the cumulative sum of our Y vowels. This line will have the label cumulative variance. Going in and setting those Y labels equal to cumulative variance and setting the tick params with axis equal to Y and label color equal to blue. Because we have two Y axes on this plot, we do need to set up a legend for each plot. Our AX1 legend will have location 0.5 to 0.5, and our AX2 will have a legend location of 0.5 by 0.4, making them stacked right on top of each other. Finally, setting our title to eigenvalues of covariance matrix, wrapping that entire thing with a PLT show. We do get this eigenvalues of our covariance matrix figure to show. We can see that our blue line represents the cumulative variance that is plotted on the right y-axis, whereas our black line represents the percentage variance and is plotted on the left y-axis. We do share a x-axis, which is mode number, represented on our traditional x-axis. This concludes Chapter 10, Part 2, Advanced Python Analysis and Plotting. Join us next time for Chapter 10, Part 2.1, where we will finish this NCEP/NCAR reanalysis example.